The question of whether humans can colonize other planets is one of the most profound and complex inquiries of our time. It touches on the essence of human ambition, our drive to explore, and our capacity to adapt to environments far beyond the cradle of Earth. The idea of establishing human settlements on distant worlds, whether Mars, the moons of Jupiter or Saturn, or even exoplanets light years away, has transitioned from the realm of science fiction to a tangible goal pursued by scientists, engineers, and visionaries. Yet, the path to planetary colonization is fraught with challenges, from technological hurdles to biological limitations, ethical dilemmas, and the sheer scale of resources required. To answer this question, we must explore the scientific, technological, and societal dimensions of interplanetary colonization, grounding our discussion in the realities of what we know today.
Humanity's urge to colonize other planets stems from a blend of survival instincts, curiosity, and ambition. Earth, while a remarkable haven for life, is not without its vulnerabilities. Natural disasters such as asteroid impacts or supervolcanic eruptions and human-induced crises like climate change or nuclear conflict pose existential risks. The late physicist Stephen Hawking famously argued that humanity must become a multiplanetary species to ensure its long-term survival, stating, "Spreading out may be the only thing that saves us from ourselves." Beyond survival, the pursuit of knowledge drives us. Planets like Mars offer clues about the origins of life, the history of our solar system, and the potential for life elsewhere. Colonization also promises technological and economic benefits, from mining rare minerals to inspiring innovations that could transform life on Earth. The most immediate candidate for colonization is Mars, often described as Earth's sister planet due to its relatively similar size and proximity. Other possibilities include the moons of Jupiter, Europa, Ganymede, and Saturn, Titan, and Enceladus, which offer unique environments, and in the distant future, exoplanets orbiting other stars. Each destination presents distinct opportunities and challenges, shaped by its distance from Earth, environmental conditions, and resource availability. To understand the feasibility of colonization, we must first examine the leading contender, Mars. Mars has captured human imagination for centuries, its reddish hue visible in the night sky long before telescopes revealed its rugged terrain. Today, thanks to missions like NASA's Perseverance rover, China's Tianwen-1, and the United Arab Emirates' Hope orbiter, we know more about Mars than ever before. Its surface features vast canyons, towering volcanoes, and evidence of ancient riverbeds, suggesting that liquid water once flowed there. These discoveries fuel speculation that Mars could have supported microbial life in the past and might still harbor it beneath its surface. Mars is not a welcoming place for humans. Its thin atmosphere, composed mostly of carbon dioxide, 95.3%, with traces of nitrogen, 2.7%, and argon, 1.6%, offers little protection from solar and cosmic radiation. At an average surface pressure of 0.6 kilopascals, less than 1% of Earth's, liquid water cannot exist on the surface, and humans would require pressurized suits or habitats to survive. Temperatures average around negative 80 degrees Fahrenheit or negative 143 degrees Celsius at the poles to 70 degrees Fahrenheit, 20 degrees Celsius near the equator during summer. Dust storms, sometimes planet-wide, can last for months, posing risks to equipment and visibility. Despite these challenges, Mars has advantages that make it a prime target for colonization. Its day, or sol, is 24.6 hours, close to Earth's, easing adaptation for human settlers. The presence of water ice in polar caps and subsurface deposits offers a potential resource for drinking, agriculture, and even fuel production through electrolysis, splitting water into hydrogen and oxygen. Martian soil, or regolith, contains minerals like iron oxides, which could be used for construction or manufacturing. These factors make Mars the most Earth-like planet in our solar system, but transforming it into a habitable environment requires overcoming immense obstacles.
The journey to Mars is the first hurdle. A one-way trip takes 6 to 9 months, depending on the alignment of Earth and Mars, which occurs roughly every 26 months during a launch window. Spacecraft must carry enough food, water, and oxygen to sustain crews for this duration, plus reserves for contingencies. Radiation exposure during transit is a significant concern, as astronauts would be exposed to galactic cosmic rays and solar particle events, increasing the risk of cancer and other health issues. NASA estimates that a round-trip mission could expose astronauts to radiation levels approaching lifetime safety limits. Once on Mars, settlers would need habitats capable of withstanding the planet's harsh conditions. These habitats must be airtight, radiation-resistant, and equipped with life support systems to provide oxygen, temperature control, and waste recycling. Current designs, like those proposed by NASA and private companies such as SpaceX, envision modular habitats made of materials like advanced composites or 3D printed regolith-based concrete. Power generation is another challenge. Solar panels are less effective on Mars due to its distance from the Sun, 1.5 astronomical units, and frequent dust storms, which can reduce efficiency. Small nuclear reactors, such as NASA's Kilopower project, offer a promising alternative, providing reliable energy for long-term operations. Food production is critical for a self-sustaining colony. Transporting food from Earth is impractical due to cost and spoilage, so Martian settlers would rely on hydroponics or aeroponics, soilless farming techniques that use nutrient-rich water or mist. Experiments on the International Space Station, ISS, have demonstrated that crops like lettuce, radishes, and wheat can grow in microgravity, but scaling these systems for a Martian colony remains untested. Genetic engineering of plants to withstand low pressure or high radiation could enhance yields, but such technologies are still in early development. Water extraction is equally vital. While Mars has abundant water ice, accessing and purifying it requires sophisticated equipment. NASA's MOXIE, Mars Oxygen In Situ Resource Utilization Experiment, tested on the Perseverance rover, successfully converted carbon dioxide into oxygen, producing 5.4 grams per hour, enough for a single astronaut to breathe for a short period. Scaling this technology to support a colony is feasible, but requires significant energy and infrastructure. The human body is not designed for life on Mars. The planet's gravity, at 38% of Earth's, poses risks to muscle mass, bone density, and cardiovascular health. Studies from the ISS, where astronauts experience microgravity, show that prolonged low-gravity environments lead to bone loss at a rate of 1 to 2% per month and muscle atrophy, even with exercise. On Mars, partial gravity might mitigate these effects, but long-term impacts remain unknown. Radiation exposure is a graver concern. Without a magnetic field like Earth's, Mars offers little protection from cosmic rays, which can damage DNA and increase cancer risk. Shielding habitats with regolith or water layers could help, but shielding during transit or outdoor activities remains challenging. Psychological health is another hurdle. The isolation, confinement, and distance from Earth, up to 250 million miles, 400 million kilometers during opposition, could strain mental well-being. Communication delays of up to 24 minutes round trip would make real-time contact with Earth impossible, fostering a sense of detachment. Studies of analog missions, such as HIS, EAS in Hawaii, or NEMO underwater habitats, show that crew cohesion, mental resilience, and structured routines are critical to preventing conflict and depression. Selecting psychologically robust settlers and designing habitats with recreational spaces could mitigate these risks, but the human psyche remains a wildcard in long-term missions. The ultimate vision for Mars colonization is terraforming, transforming the planet to resemble Earth. This would involve thickening the atmosphere, warming the surface, and creating conditions for liquid water and breathable air. Proposals include releasing greenhouse gases like methane or chlorofluorocarbons to trap heat, detonating nuclear devices to melt polar ice caps, or deploying massive orbital mirrors to reflect sunlight. However, these ideas face enormous practical and ethical barriers. Mars's low gravity would struggle to retain a thick atmosphere, and the resources required for terraforming exceed current technological capabilities. Estimates suggest that even partial terraforming could take centuries or millennia, assuming it's feasible at all. For now, colonization efforts focus on enclosed habitats rather than planetary-scale engineering. While Mars is the most immediate target,
other celestial bodies offer potential for colonization, each with unique challenges and opportunities.
Earth's moon, only 3 days away by spacecraft, is a logical testing ground for colonization technologies. NASA's Artemis program aims to establish a lunar base by the late 2020s, with plans for a gateway space station in lunar orbit. The moon's low gravity, 16% of Earth's, and lack of atmosphere present similar challenges to Mars, but its proximity allows for easier resupply and emergency evacuations. Water ice in permanently shadowed craters at the lunar poles could support life and fuel production. However, the moon's barren surface and 14-day cycles of light and darkness complicate long-term habitation. A lunar colony could serve as a proving ground for Mars-bound technologies, but its limited resources make it less viable for large-scale settlement. Jupiter's moon, Europa, is a tantalizing target due to its subsurface ocean, estimated to contain more water than all of Earth's oceans combined. This ocean, locked beneath 10 to 20 miles, 16 to 32 kilometers of ice, could harbor microbial life, making Europa a priority for astrobiology. However, Jupiter's intense radiation belt bombards Europa with high-energy particles, requiring heavily shielded habitats. Drilling through the ice to access water would be a monumental engineering challenge, and the moon's low gravity, 13% of Earth's, poses similar health risks to Mars. Ganymede, the largest moon in the solar system, offers a magnetic field that partially shields it from Jupiter's radiation. Its surface contains water ice and possibly a subsurface ocean, but its distance from Earth, about 390 million miles or 628 million kilometers, makes missions logistically complex. Both moons are far from practical colonization targets, but could host research outposts in the distant future. Titan, Saturn's largest moon, is unique for its thick atmosphere, 1.5 times denser than Earth's, and stable bodies of surface liquid, including lakes of methane and ethane. Its nitrogen-rich atmosphere and organic compounds make it a candidate for studying prebiotic chemistry, but its extreme cold, minus 290 degrees Fahrenheit or minus 179 degrees Celsius, and distance, 800 million miles or 1.3 billion kilometers, pose significant barriers. Titan's low gravity, 14% of Earth's, and lack of breathable oxygen require enclosed habitats, but its atmosphere could provide raw materials for fuel or plastics. Enceladus, a smaller moon, has geysers that eject water vapor and organic molecules from a subsurface ocean, suggesting potential habitability. Like Europa, its distance and radiation environment make colonization impractical for now, but it could support scientific missions. Venus, Earth's closest planetary neighbor, is often overlooked due to its extreme conditions: surface temperatures of 900 degrees Fahrenheit or 475 degrees Celsius, pressures 90 times Earth's, and an atmosphere of carbon dioxide laced with sulfuric acid clouds. However, floating habitats in Venus's upper atmosphere at altitudes of 30 to 35 miles, 50 to 55 kilometers, could exploit a region where temperatures and pressures resemble Earth's. These cloud cities would require advanced materials to withstand acid corrosion and reliable buoyancy systems. While intriguing, Venus remains a speculative target compared to Mars. Beyond our solar system, exoplanets orbiting other stars offer the ultimate frontier. Over 5,000 exoplanets have been confirmed, some in the habitable zone where liquid water could exist. Proxima Centauri b, 4.2 light-years away, is the closest known exoplanet, but its habitability is uncertain due to its star's frequent flares. Interstellar travel, requiring speeds approaching a fraction of light speed, remains beyond our grasp. Concepts like laser-propelled sails, e.g. breakthrough starshot, or generation ships are theoretical, and even optimistic timelines place such missions centuries away. For now, exoplanet colonization is a distant dream, limited by energy requirements and our understanding of alien environments. Societal and ethical considerations. Colonizing other planets raises profound ethical questions. Who gets to go? How do we ensure equitable access to opportunities in space? Private companies like SpaceX, Blue Origin, and others are driving the push for colonization, but their profit-driven models risk prioritizing wealthy elites over broader societal benefits. International cooperation, as seen in the ISS, could ensure shared responsibility, but geopolitical tensions may complicate efforts.
The Outer Space Treaty of 1967 prohibits claiming celestial bodies for national sovereignty, but it's unclear how this applies to private entities or resource extraction. Environmental ethics also come into play. Mars and other bodies may harbor microbial life, and human presence could contaminate these environments, undermining scientific study or ethical principles of non-interference. Terraforming raises questions about our right to alter another planet's ecosystem, even if it's lifeless. On Earth, colonization efforts must address the carbon footprint of space launches, which emit significant greenhouse gases. Economic feasibility is another hurdle. A single Mars mission could cost hundreds of billions of dollars, and a self-sustaining colony would require sustained investment. Public support for such endeavors may wane if immediate benefits are unclear. However, history shows that exploration often yields unexpected rewards, from technological advancements to cultural inspiration. The question of whether humans can colonize other planets is not a simple yes or no. Mars is the most feasible target in the near term, with technologies like reusable rockets, SpaceX's Starship, in situ resource utilization, and advanced life support systems making small-scale settlements plausible within decades. NASA's Artemis program and SpaceX's ambitious plans for Mars missions by the 2030s suggest that initial human outposts are achievable, though self-sustaining colonies will require breakthroughs in energy, food production, and health management. Beyond Mars, the Moon could serve as a stepping stone, while Jupiter's and Saturn's moons are longer-term prospects for research outposts. Venus and exoplanets remain speculative, limited by distance and environmental extremes. Each destination demands tailored solutions, from radiation shielding to resource extraction, and no single approach will suffice. The greatest barriers are not just technological, but human. Can we muster the political will, economic resources, and ethical clarity to pursue colonization responsibly? Can we adapt physically and psychologically to alien worlds? The answers depend on our ability to innovate, cooperate, and balance ambition with humility. Humanity stands at a crossroads. Colonizing other planets is no longer a fantasy, but a goal within reach if we can overcome the formidable challenges. Mars offers the best chance for near-term settlement, leveraging its resources and relative proximity. Other destinations, from the Moon to distant moons and exoplanets, push the boundaries of what's possible, demanding centuries of progress. The endeavor will test our ingenuity, resilience, and values, forcing us to confront what it means to be human in the vastness of the cosmos. As we gaze at the stars, we are reminded of our history as explorers, from ancient seafarers to astronauts walking on the Moon. The question is not just whether we can colonize other planets, but whether we will, and what kind of future we will build among the stars. The journey has begun, and the universe awaits.